Good morning and happy Wednesday. Thank you for joining us. We are Heron Innovators. We're home of the suspended air flotation. If this is your first time joining us, I just want to note again that this is all new to us. So bear with us with any technical difficulties or issues we might have. This is, day 3 for us now. So hopefully we've worked out those kinks and we have no issues. But just in case, I want to note that there's a chat feature at the bottom of the screen. If you have any questions or you can't hear us or any kind of issues along the way, please feel free to use that chat. We're actively watching it and checking it to make sure everything's running smoothly. Again, I want to introduce ourselves. We are Heron Innovators, home of the suspended air flotation. My name is Andrea Hofstetter, and I am joined today with the president of Heron Innovators, John Barsotti. We also have with us remotely Jeff Knolenberg. He is in Kentucky, and unfortunately he is under a COVID quarantine. So, he just has to kind of join us in this new adventure in the remote world that we're all now learning how to live through. So with that, I will go ahead and turn it over to John to kind of introduce himself, and then we can go ahead and get started.
Thank you, Andrea. Yeah, as Andrea said, my name is John Barsotti. I'm the president and founder of Heron Innovators. I started this company in 1997 in one of our employees' backyard, actually. So today we have more than 100 installations, and we're particularly good at algae. Again, I wanted to thank you all for joining us. I know this is a tough time. This is not the way we would like to do this. We often really like to be face-to-face with our customers. We are usually face-to-face with our customers, and can actually talk to you specifically about your specific condition. But all that's gone, all that interaction's gone here, and it's pretty difficult for us. So we are likely to miss some things in this presentation, so please take advantage of that chat feature and let us know if you have questions, and I'm sure we'll fill in the blanks for you. Again, I want to thank you for joining us in this era of COVID. I'm hoping that all that is going as well as it can for all of you that are watching. In a minute, Jeff will come on, and he's our Vice President of Sales. He will introduce himself briefly, and then we will get into the presentation, which is about algae today, something we do particularly well, we believe. All right, Jeff, that's you.
Thank you, John.
Yeah.
Thank you, Andrea. So yeah, my name is Jeff Knolenberg, coming to you live from Kentucky. And in fact, I've got my last day of quarantine tomorrow, so I'm looking forward to getting out in public again. One more day to go. But so our topic this morning is easy solution to a persistent problem, algae. And so what we're going to do this morning is talk about what is that problem, talk about in both water and drinking water as well as wastewater plants, what kind of problems that we've seen. And of course, as John said, if you've got any questions about that or have specific problems you've encountered with algae, please send that to us through the chat feature. And then after we define that, we're going to be talking about SAF technology, how it works. And then we're going to be talking about SAF as applied to algae. And we'll be going through some case studies and hopefully have some informative things to share with you. So, John, let's talk about algae.
Okay.
As I said, both wastewater and drinking water plants tend to struggle with algae. And often I'm at conferences, and as I'm sure you probably are as well, and this seems to be a recurring topic. It's creating problems with other technologies that are out there. And I always, at those conferences, wish I could stand up and tell people about SAF. So I guess now's our opportunity. So let's first talk about just what are those problems? What have you seen, John?
Well, algae tends to float and sink, so in the use of clarifiers, it can be problematic to think of it. So, most on the municipal side, even in the industrial side, it has to do with treating the water, treating the BOD. The water, in the municipal side, it's often in a holding pond after the water's been treated. It has some residence time there, and they're waiting to reclaim it. Here in Title 22, we have a regulation called, here in California, we have a regulation called Title 22 for that specific application. Otherwise, for industrial clients or other applications where you don't have to worry about pathogens and that sort of thing. The clarity of the water can be important for preventing, drip irrigators from blocking and so on and so forth. So we have a number of needs to treat algae, and settling in a clarifier isn't always a good option. Although there's been some success in slot plate settlers with a little bit of chemistry, by and large, flotation or filtration is what's used, and the water oftentimes has too much algae to support just a straight filtration program. In fact, here in California, Title 22, only, to my knowledge, only has approved filtration of different types as a Title 22 certified treatment systems. So we are in a position where we're pre-treating to a filter. Oftentimes, DAFs and SAFs are used in front of that. Sometimes clarifiers. So we are kind of uniquely suited for this. We believe we at about a third the chemistry of a DAF. Lot less horsepower, a lot smaller footprint. We're achieving, 0.2 to point. We got 2-3 examples, 0.2 to 0.3 NTU water. If this is a wastewater application of some sort, whether it's industrial or not. In the primary water, we're always under 2. That's growing algae. We have a few applications out there that when we're not in wastewater, we're in primary water of some sort, and we're trying to treat algae, and sometimes some very high concentrations, 400 to 600 parts per million algae. And even then, we get it to something under 2 NTU, and that's a couple parts per million, 3 parts per million. So on top of that, we float the solids particularly well, and we get and they easily to water because of the way we handle it. So I'm gonna stop talking now for a minute and let Jeff jump in here. I realize I got about 3 of my segments in the one caption there. So Jeff, roll. Save me, Jeff.
The challenge in front of a drinking water plant with algae blooms. What kind of problem is that specifically causing in those facilities?
It is the same problem, Jeff. It is in every case in a drinking water plant using surface water, there's a filter in the network that's treating the water, taking all the suspended solids, turbidity basically out of the water and then it follows either, it just depends on the water, but it could be like a powder activated carbon treatment system downstream, or go right to disinfection. But eventually there's a disinfection step, and in order for that filter to the filter blinds like they normally do, and those cycle times can be, when there's algae in the water, it can be particularly tough, and it can be actually particularly tough to regenerate the filter, as the algae has a tendency to bind the media a lot tighter than silt and other medias. So there's been a class of filter that's, if you will, that's come out that has some sort of pre-treatment to the filter built into the design. And these are, they're slotted clarifiers of some sort. They add a little chemistry in the front end, and they try to settle the solids before it reaches the filter. Again, a lot of the algae just wants to float, so that can be a tough option, because you still can get a lot of algae to the filter and have all those same problems you had before. And so in the few applications we've been in front of a filter in a drinking water application, we've extended the cycle times of the filters for a very long time, sometimes days. Back at you,
very
John.
good.
Yeah.
So tell you what, I've got a few slides I'd like to pull up and go through SAF Technology. I think it'd be good at this point to go through that so we can talk about how that's applied to solve this problem. And can you see the slides?
Yep. Yes, we can.
Okay, so I'm going to start off with a jar test that John and I were involved with many years ago. This was really one of the first times I met John. This was about 3-4 years before I went to work for Heron Innovators. I come from the centrifuge world, and I was walking a trade show, ran across a chemical vendor at a trade show booth, and he mentioned SAF to me. I was trying to figure out how to better break emulsions coming off of DAFs, or dissolved air flotation, And he mentioned SAF. He said it could actually use less polymer than what a DAF uses, which piqued my interest. I'm thinking polymer's creating an emulsion. I'm trying to break the emulsion centrifugally, and I'm thinking less would maybe help. So I gave John a call. We started talking about SAF, and I started learning about this. I thought, wow, this is a heck of a technology. I need to learn more. And I invited John to come out to a poultry plant in Arkansas, and we grabbed samples all morning long from various points and various plants, and went back to a lab. So what you see on your screen is one of those jar tests. This came from a wet well that had gone septic. It had sat for several days, and this was some pretty nasty water. It did not smell good. And so what you're seeing in the picture is in the jar, and this is probably around 3,000 ppm of TSS. There's a little bit of coagulant, there's just a little bit of polymer, and we've got a pin flot for it. And I'm going to start this video. This is a tube coming from a SAF lab unit, a SAF generator lab unit. And that's John standing in the background. So what you see is there's a charged micro froth, charged microbubble froth being injected, and those bubbles are attaching to the solids, getting a very high removal rate, very fast rise rate, and a very stable float. And that caught our attention. I had both the lab manager as well as the and I think he said, wow, that was really something. And he started looking into SAF. In fact, visited 3 installations, Missouri, I think we went to Dodge City, Kansas, and we also went out to Fairfield, California, where SAF was installed, and really were impressed with what we saw in that particular plant. In fact, now owns 9 SAF systems. They've converted most of their DAFs over to SAF now. Which that's a big part of Heron's business, is converting DAFs to SAF, but they also own a lot of new SAF systems too, which we may get into a little bit more here. So let's start defining how SAF actually works. You know, at first glance, this is just another flotation technology. It doesn't appear to be a whole lot different than dissolved air flotation. If you were walking to a room and look at it, you wouldn't know that you're really seeing a different technology, because they're both flotation. You've got a big vessel sitting here where you're floating solids out of water. So I'm going to start off defining. As you dig into this, when you really dig into it, it's a very different technology. Circulation system typically, where you're drawing from the underflow, and that's theoretically where the water is cleaner. So you're pulling from the underflow with a recirc pump, pushing against back pressure, injecting compressed air. Under pressure, air dissolves in water up to the saturation point. What that saturation point is basic physics. The temperature, pressure, all that's going to affect how much air you can squeeze into that water. And then when that water re-enters the flotation cell, now you're at a lower pressure, so you've exceeded saturation point. So the little bitty soda pop bubbles are going to come out of solution and work to float the solid to the surface. Often you're adding in water, to break the solid. The technology's actually been around for over 100 years. Of course, over that time, there's different ways of sparging in more air. They're all creating bubbles in the water. That there's really nothing special about that bubble. And I'm going to ask John here in a minute to talk about those bubbles. What makes SAF bubbles so different from DAF bubbles? In fact, that froth. So what DAF doesn't stick. It instead of making bubbles the way we just described, it's going to create a charged microbubble froth with a froth generator. And this sits somewhere in the vicinity of the flotation cell. It's a small unit, about 4x4, 4x6 foot footprint unit we have, size of the application. But a really small unit sitting somewhere nearby, and this froth is going to be 40% air by volume. With the DAF, we're talking about 2 to 4% air at most. But this is 40% air, and these bubbles are 7 to 25 microns in size, which is a much smaller bubble. They resist coalescing, but these bubbles, as I said, are much different than what DAF bubbles are. And so, John, why don't you talk about that a little bit? What makes SAF bubbles so much different than DAF bubbles?
Well, SAF bubbles are actually been patented in the 70s, called Afrons. They're used often in the mining industry. The whole process was supposed to, in the 70s when it was patented, was supposed to scale into this DAF application. It's actually what we brought to the table. Is in the 90s we learned how to scale this. The original inventors all actually passed before the technology was ever used. The bubble itself is a double-walled surfactant bubble, and it doesn't coalesce readily, which is very helpful in these water treatment applications because the bubbles remain in solution for minutes, available for use by solids, right? The surface tension, we have a surfactant on the outside of that bubble, a surfactant sheath, and that gives us surface tension advantages to a DAF bubble. So that actually overcomes the surface tension of the particle, binds the particle just far more readily. In addition, we have electrostatic attraction properties. We can use a cation or anionic surfactant to bind the particle. There's almost always the need for an anionic charge. And that binds the particle tightly. We get a lot of air in there. We don't have the resistance to binding that a DAF bubble would have. And the bubble is 7 to 25 microns in diameter. It has a slight charge to it. It acts a bit like a coagulant on top of it all. So you actually, in the video, if you look closely in that jar test, you actually see when we added the froth how that particle just puffed up, right? And it actually flocculated or coagulated in addition to what polymer and coagulant had done before us. It's in that we save a lot of chemistry. It's not unusual, especially in a municipal setting, to see 70% less chemistry because of our process. And in algae specifically, we run about a third the chemistry of a DAF. Jeff?
Yeah, thank you, John. So if you can see the slides, are we still on the slides?
Yes.
We're there. Yep.
So the froth, here's the froth generator, and that's where we're making those bubbles. They're actually injected ahead of the flotation cell, and they're going to be stirred in ahead of the flotation cell. So different from a DAF where air is continually being fed to keep that solids blanket suspended on the surface, there's going to be no more air injected after we put it into here because the bubbles are actually attaching to the solids. In fact, this shows we've got a mixer that will be in front of the flotation cell. So the froth's injected here, these bubbles are going up with the influent and being entrained and gently stirred in with this paddle mixer. Of course, this drive is VFD controlled. It's probably turning at a rate of around 10-15 RPM. So very gently stirring that in to get that air to particle reaction. And the reason I keep emphasizing gently is because what we do not want to do is shear the flock that was created with the chemistry, which is actually one of the disadvantages of a recirculation whitewater system, because that pump will actually macerate the solids that were created previously with the chemistry. So starting up a DAF is much more difficult because of that reason, where this instantly we're making good froth. This system is up and going within just a few seconds of hitting a start button. So again, froth's injected into this point right here, and then it goes into the flotation cell where again you'll see that very fast rise rate, and it just creates a very stable float. And in fact, drier solids, right, John?
Yeah, so the density of the solids is much less than you get in typical DAF applications or IAF applications. And that density creates, we have nothing like a rag layer, right? The solids are formed, they float right to the top, and they clearly sit above the water, which makes them perfect for draining, right? So they drain water, and we get very close to meeting paint filter tests all the time in our solids. They also have, maybe a little bit of a sideline, is they have kind of a gelatin property to it when they come off, and with that property, it really serves downstream dewatering well. We release some fabrics really well. We have a fluid component to it, even though it's very dry, for like screens and so on and so forth. So downstream dewatering oftentimes does far better with a lot less chemistry and a lot less maintenance, given that the solids have come from our process.
Yeah, in fact, John, I've got a few pictures of getting away from the diagram. Let's look at actual SAF systems. So if you would, walk us through what we're seeing here.
Yeah, so the screen I'm looking at is a little bit above the camera, so if it appears to you out there that I'm looking over your head, I'm actually looking at a screen I have here. But on the top left corner, there is that mixer that Jeff was showing you earlier is actually there on one of our float cells, right? And so the water comes into the middle of that mixer, and it splits the two nozzles that feed into the tank. You can see the gear motor there that's VFD controlled. VFD, of course, is in the control cabinet, and that helps us to mix that the flockade or the froth, the micro froth, evenly and gently and as close to instantly as we can. Right? On the right side is actually the SAF generator, and that's our secret sauce, right? That is a proprietary piece of this whole thing. That unit is able to deliver 7 to 25 microns at whatever flow rate you want, as long as it's within the spec of the unit you purchased. So there's just actually like a diaphragm valve, like a water valve there, and you can turn up, send more air to the process or less air to the process. In addition, there are, water level in that can is maintained through a float switch, and flockade feed to that can is maintained by the flow meter, right? So it's pulse fed from the flow meter feeding froth out. So really, the difference between a lot more air and a lot less air is just turning a valve. Everything else adjusts itself. On the bottom, you got a traditional flock tube we use. If you're just feeding polymer, we probably don't use but the last 10 feet of that or so. Almost in all our installations, polymer's fed 1 or 2 spaces immediately before it goes into the mixer. So the flock tube mainly becomes for giving you resonance time and mix energy for the purpose of coagulation and the purposes of pH control if you need to do that. And on the right side is just another shot of that same float cell you're looking at in the top left. That's a CF1000 float cell. It has, that's our CF1000 float cell, I should say. And that has 140 square feet of float area. It runs 2,800 gallons a minute in thousands of parts per million solids. It's in operation right now. We get high 90% removal. In the poultry industry, we see right at about 30% solids coming off the top of that. Jeff?
Yeah, so thank you, John. And just to, I think it was appearance, but just to be sure that, so the water's coming in through the serpentine. This is where the chemistry addition takes place as far as coagulants and then polymer. And then that water is flowing this direction, and it's coming right here off the serpentine. On this model, it's actually splitting 2 directions, and the froth is injected right here. So the froth generator is actually sitting behind this unit. Froth is injected right here. That water, so now we've got the influent water, froth injected, and it's being stirred in by that mixer right here, and then it goes into the flotation cell. Effluent comes off the other side. The clean water comes out the other side, and then of course there's a rake on top that's raking the solids to fall down into this vessel right here, where this particular plant, they're actually doing a second dewatering step just with gravity drainage. And John, that's one thing. In fact, we're going to play a video in a little bit where you're going to see how dry algae can get, how dewatered it will get. But this particular plant takes advantage of first the fact that the the solids float so well, they just leave them up on the surface for a really long time. They slow that rake down, and we can put the rake on a timer and not even rake for, let's say sit for 10 minutes and then rake for another couple minutes. And then it goes here. This plant, as I said, they do a secondary gravity decantation where they've got a ball valve they'll just crack open every few hours. And then, of course, the solids pump will, after they decanted it, the solids pump sends it on its way. So let's talk about algae. And this video was actually shot just a few months ago at a trial that was done, I think, in Northern California, right, John?
Yeah, it was. It was in City Colfax, right? Yeah, so that's algae.
Yeah.
It's growing in primary water, Jeff. So that's one of the applications I didn't actually talk about. But a lot of these sewer plants, when they have high flow conditions, they get a lot of infiltration, and it exceeds the hydraulic capacity of the wastewater treatment plant. And so the water is diverted into a pond, basin, EQ, a number of places. But often those places almost always, those places are open to sunlight, and they grow algae. And so it becomes very difficult for the plant to receive that and then send it to the process. So they have to pre-treat it, or it's helpful to pre-treat it. And that's where we come in, and that's the position this video had us in at that time. Right, and we've also done this up in Fort We've done this in a few plants. It works very well.
What kind of numbers were you seeing there? Turbidity levels?
I believe it was right around 1 NTU, right? About a half to 1 NTU. I got to go back and look. I'm sorry, I wasn't ready to. But it was pretty low. It was very low, and it certainly was low enough to be incorporated into the rest of the plant without concern.
Yeah, I just thought I'd also mention, John, when I first started talking with you years ago, you were just kind of finishing up some pilot work that you did with some startup companies that were trying to take algae and convert that to biofuels. I know there was a number of those a number of years back that were trying to as I said, make fuel from algae. And even though that industry maybe wasn't quite so successful, I think the pilot work you did, the numbers I remember you telling me were pretty impressive. Do you remember any of those?
Sure. Well, there's one particularly in well, we did 2 of them, and we're involved 2 of them to some extended degree. One was in Daphne, Alabama. We were actually there for a little bit over 2 years. And what that project was is they were inoculating primary sewage with algae, and the water was being sent out to 6,000, then later 10,000 gallon bladders in the bay. And the sunlight would grow algae. The algae would oxygenate the water, degrade the primary solids. That would be pumped back to the plant on shore, and we would harvest that algae. And in that application, we saw 400 to 600 parts per million algae. We were, constantly under 2 NTU and about 7 to 10% solids, which they had spent, $250,000, $500,000 in trying to find an answer to that, with 2 or 3 different approaches failing. In that application, our dewatered solids would go into a high pressure, high temperature liquefaction process with the intent of creating kerosene, basically, with what they could. So, and as what happens with a lot of those, it's just hard to grow enough algae to make it worthwhile to get enough yield. So then another application wasn't for biofuels, but another plant here in California uses algae to aerate the water. It's the acronym escapes me. I think it's APIX, but basically the algae is on a raceway around the plant. It takes primary water and it's treating it, and the algae is the only aeration process available to the water. And again, those solids get into the 400 to 600 part per million range, and it's almost all algae. And we treated those and got, again, down something under 2 NTU, far exceeded the incoming water to the plant, and made it, the water was easily treated downstream of that. And it actually gives a high rate option to either harvesting or just treating algae, right? So, most of these clarifiers, they can't receive more than a few gallons per square foot per minute, and we are we're sitting there at 20 gallons a minute per square foot per minute. So.
Yeah, so John, you mentioned Title 22 water, and in a minute here, we're going to play that video that we put together about Grayton, California. First, before we get into that, can you tell us a little bit more for those that may not be familiar with what Title 22 means? Can you kind of go through that a little bit to set this video up?
Yeah, sure. So Title 22 is the California requirement for reclaiming water from wastewater. So any municipal plant that's treating wastewater that wants to reclaim the water has to meet this specification and eventually get the approval of the regional boards, the various regional boards up and down the state. The challenge is that, the data shows that, and the regulation states that the filter, the Title 22 approved filter, has to achieve less than 2 NTU before disinfection, and that's to achieve, I believe, that 4-log pathogen removal that they're trying to hit. And the filter can do that, but the filters have trouble with algae, and algae binds the media or whatever, tightly, doesn't come off of it easily on regen, it blinds it quickly, and so there's a need for pre-treatment, and the clarifiers tend to take a lot of space, and again, like I said earlier, some of that algae wants to float, so it's particularly hard to get it to settle. So these flotation approaches are attractive, and ours is probably the best suited. DAFs are kind of find algae treatment difficult, in that first of all, the percent solids coming off the top is very thin. 1% algae on the top of a DAF is considered, it's oftentimes these very low numbers, 0.5%, 1%. I don't think I've ever even heard of anything achieving over 2%. Well, we're always in the 7 to 10% range, where a DAF will warranty maybe, and even we were asked to do this, a 10 NTU result. Today, not on this video, but today we guarantee a 5 NTU result, and we are always under 1 NTU. In fact, all our customers will tell you they can pretty much manipulate the chemistry to be somewhere between for our discharge to be somewhere between 0.2 and about 0.8 NTU. Well, we're only trying to get through the filter to 2, so that takes a big load off the filter, and the cycle times really get to be pretty long. And the other point to make is we do this all with about a third the chemistry of DAF. How's that?
Well, I think you more than explained what Title 22 is.
Okay.
So, let's jump into the video.
Got it.
I serve the District of Grayton as their general manager. I'm a contract general manager. I've worked in the field 37 years. Grayton is a unique environment. It's got beautiful wildlife resources, and it had been run down by the previous management. The people of Grayton decided to take over and form their own special district and revitalize it. They inherited some problems, one of which is Grayton would not be allowed to continue to discharge into the Atascadero Creek. We actually conducted a pilot study here at Grayton, full scale, and we proved to the state that we could get the required removal of algae and bacteria from the water with a SAF to get turbidities down in the 10 range or lower. Pete Lescure and I were working with the district to try to find alternatives to going to this activated sludge or regional system.
With the lead designers on this Grayton wastewater project, I was convinced from the viewpoint of the principals that whereas a DAF, you have to backtrack, recycle 50% of what you're trying to produce, the SAF only has to use 2% of that flow. So that means a whole lot less pumping you're doing. That's a whole lot less material handling you're doing. smaller pipes to deal with, etc.
The SAF unit takes water from our ponds and adds coagulant to it in this mixing tank and conveys it to the bottom of this SAF unit where a surfactant and air are entrained and cause the algae and bacteria to float to the surface. When they get to the surface, they're collected by this scraper and carried all the way to the end of the SAF unit where they are brought up on a beach. The water drains off and the solids fall into a bin. The bin then is dewatered by gravity and it is composted. People don't always want something new. Do we need to continue with things that were developed in 1911 that are shown to be less efficient than things that are now available in industry? I believe not. And we'd like to show them it's okay.
Yeah, so Grayton was one of our first algae projects. You know, we did a trial there and we achieved numbers that no one knew could be done with a flotation cell. So it turns out to be a pretty useful video for us. We've come a long way since then, and our processes are better, more automated. But the fundamentals of what we use there are the same we use everywhere else. So I'm going to turn this back over to Jeff
Yeah, I think so. Grayton's a great example. That's a system that's been running a number of years. Pleasant Valley State Prison is another, right?
That's correct. And so that's a newer system, right? So that went in a couple of years ago, I'm going to say 2018, 2017. And that, again, you know, we duplicated that really low polymer and chemical consumption. But we did a few things a little bit better. And so we're getting, it's not too hard to achieve drinking water performance in that unit. And I mean, the sites, like most sites, they just think they're so easy to run. The operators love them. So we had an operator at another site just recently, Jeff, as you know, say these things are stupid easy to run. They are, and if you do something, if you're playing with it and it falls out of specification, it's just so easy to get it back, and it gets back quickly, like in minutes, not hours or a day, right? So back at you, Jeff.
Thank you. So one other story I recall you telling me is that the chemistry vendor for Grayton, I believe it was, actually mentioned to you that he had other technologies running in other plants, other flotation technologies, probably mainly DAFs. And talk a little bit about that, what you told me he said.
Well, basically, the conversation.
It was about how much polymer we used compared to what they used.
The chemistry, the chemistry in general, right? So this is a Salinus rep, and we were coming under fire because we were using polymer, and the downstream filter was trying to blame some of the trouble they were having on the polymer. So of course I brought in some experts, and what we found out is that we shouldn't be having a problem until like some significant, like almost 10 times what we were feeding. But then the other thing we found out is in the DAFs running up and down the state, we were using that's where I get about the third of the polymer. And not only that, if you wanted to wet the solids a little bit, you didn't need to get under 1 NTU. You're okay with 1 or 2 NTU. We could go maybe even half that. So right now, both those installations are running at about a third of a DAF and are both achieving, somewhere between 0.2 and about 1 NTU.
Speak a little bit to obviously we said we use a surfactant to create the bubbles, and certainly there's residual amounts of that surfactant left in either the solids or the water that's coming off of the system. Common that I know a common question both you and I get is, how does that affect downstream processes?
So we have not found any negative impact to anything downstream, whether it be the water or the solids. And both have been tested extensively. So in the case of the water, there's a test called MBAS, which is methylene blue activated substances. It's a general measure of anionic surfactants in solution. And every time someone's bothered to look at that, we've we've taken out about half the MBAS out of solutions. There's just a lot more naturally occurring anionic surfactants than we are putting in solution, and we are taking them out, some of them out. So, and then in the solids, it's always, oftentimes it's the folks with the digesters that are worried about foaming. And in the few applications where we're feeding to a digester where we've actually turned over the entire volume of the digester, we may have even helped the foaming situation. We certainly didn't make it any worse.
Yeah, and just to add, drinking water, the surfactant is NSF approved, right, John?
It's NSF approved, it's non-toxic, non-hazardous. I guess I should have said that as well, right? Non-toxic, non-hazardous, and we are NSF approved for drinking water uses.
Well, Andrea, I'm going to turn things back to you. Have we had any questions come in?
We have had a few questions come in. Let's see. The first one being, how does SAF deal with the toxicity to algae?
So, recently in the last several years, we've been seeing a lot of toxic species of algae growing in waterways and surface waters. And to date, we haven't had a trouble with any species of algae. We can treat algae and we can pull the algae out. I don't know what we can do with regard to a dissolved toxin in solution. I know that we are oftentimes looked at to measure total organic carbon removal, and they want to see, people want to see like 30% TOC removal, and we seem to do that readily in drinking water applications, and we certainly can get the algae out. We don't have, unlike many people where they try to get into the difficulties of various species of algae, it seems like our surfactant and our froth is able to overcome all those nuances, and we just can treat algae, and we can treat it well. Next question.
Great, thank you, John. And the next question is, can the algae dewater enough via gravity to be land applied?
It can. We get to 7 to 10% solids right now, and it goes to landfill. It's actually free of all. It meets a paint filter test, and so that can be land applied. The issues with land applying are kind of different. Especially from a wastewater application, we need to meet the class 1 or class 2 kind of solid, class A, class B solids for EPA, and so there's issues with that, but certainly from a dryness perspective, they can be land applied, and they can still be pumped. We can render them at whatever level of dewateredness you might need, so that you can apply it as you need.
Wonderful.
Yeah.
Thank you, John.
Yeah.
So I think those were all the questions that came in. What is a paint filter test? I guess there's a...
So the paint filter
last
test is just a way to measure the free-flowing liquid that's left in the solid. So literally, they use a paint filter, and the solids are put in there, and no water can escape the filter. So, okay.
Interesting.
Yeah, and that's a test they do for landfills, so they don't get materials that flow readily around the landfill. So,
Okay,
yeah.
great. Well, I want to thank you both gentlemen for the presentation today, and thank all of you for joining us. Again, we are Heron Innovators, home of the SAF. Any questions or any way you want to ever reach out to us, you can at any time. Our email address is info@heroninnovators.com, or you can check us out on our website at www.heroninnovators.com. Thank you again, and everybody have a wonderful Wednesday.
Thank you. Bye for now.